Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 11, Section 3, Part 1. So in this chapter, we're discussing situations where the outcome variable y takes on the values of 0 and 1. And you can think of that as success and failure. You can think about the one denoting some sort of event that a person has, and a 0 means that they did not have that event. And then the x's are explanatory variables. And so we're going to model the table that we see on page 293, table 11.1. Trisomy and maternal age among spontaneous abortions. Okay, so in this model, we have X being the coded age, and so those are showing you the groupings. You have the number of trisomic karyotypes, and I just called that trikaryotypes here. And then the number of normal karyotypes. All right, so essentially what I'm doing here is I'm going to run that in to R, and then I'm going to create a data frame by using this cbind of those three variables that we just mentioned. And then on the outside of that function, I'm going to use this as.data frame. So when I look at my final data set, it should look very similar to table 11.1. It's a subset of that table. All right, we would also like to calculate the total, which is just the summation of the trisomic karyotypes and the normal karyotypes. So here I create a new variable, data $total. So if I look back at my data set, now I have one additional column with the total trisomy plus the normal karyotypes. And then I can get the proportion by taking the division of the number of trisomic karyotypes divided by the total. And from here, what I want to do is I want to actually expand out this data set so that instead of being in this table form, it's going to give me a long data set. So what I'm going to do is I'm going to create a list, and I'm going to just put an empty list in for a list called my list. And then we have 6 rows in this table. So that's why this for loop is going to go from 1 to 6. And what I'm going to do is I'm going to use the repeat function. So I'm going to repeat my X value for the number of trisomy karyotypes that we have. And then I'm going to repeat this same X number for the normal karyotypes that we have. Okay, that's going to give us our long form of X. All right, then I'm going to get a long form of an indicator variable, which will take the value of 1 when a trisomic karyotype occurs, and a value of 0 when it's a normal karyotype. And at the end of the day, I'm going to bind together that X expanded and the tri-dot expanded. So let's run this for loop, initializing the list at the start. And now what I'm going to do is I'm going to be left with just this list, and I'm going to paste together that list in one thing. Before I do that, I just want to show you one example. So let's look at the first thing in the list. Remember, the list is 6 long. I use the double brackets in this case because it is a list. Okay, so now you notice that there should be a total of 79 rows, right? And if I look at this, I have 2.5 repeated 9 times because that was the number of trisomic karyotypes. And then I have negative 2.5 repeated 70 times, which gives me a total of 79 rows. So I'm getting the long form of my X variable and then the indicator for whether or not the trisomy occurred. Okay, so what I'm going to do is I'm going to create a new data frame called temp, and it is going to have the long form of table 11-1. All right, looking at the first 10 rows, I see the first 9 are trisomy. After that, a normal karyotype starting at -2.5. If I looked at the tail of this data set, that should give me the X value of 2.5 at the very end rather than -2.5. So this is giving me the last 6 rows, and that's looking good so far. And if you notice, we have 756 rows now in our data set, right? You could just check the dimension of your new data frame called temp for now, right? So we have 756 rows by 2 columns. So that's giving us our X and then our Y. And since our Y takes on a 0, 1 value, we can use a logistic regression model to model whether or not there was a trisomic karyotype and model that based on age. So we're going to use this GLM function. And in the GLM function, we in general have the setup where we say Y follows X. We tell it the data set. We're going to tell it the family equals binomial. That's going to tell R that you'd like to do logistic regression. So we're going to do the fit for our GLM. And here we get the intercept and we get the coefficient related to age. And if we wanted to just explore what we're able to pick off of that fit.glm object, we can do names of fit.glm. And here's all the things that I could put attached to the fit.glm using a $sign. So for example, if I did fit.glm $sign coefficients, that should give me a coefficients table. Similarly, if I do fit $sign weights, now I'm going to get each of the weights that are associated with every observation. So if we move on, you'll notice in equations 11.6 through 11.11, there's a lot of things that we could pick up from our modeling to make these calculations a little more straightforward. We're going to do it where we pretend like we'd have to hard code these equations. So essentially, I'm going to first get your summation I equals 1 to n of the WIs, right? That's just going to give you the denominator of the first term that you're going to need for your estimated standard error for the y-intercept, right? So here's our sum of WI. We're just summing up the weights. Okay, we can get our X bar W, and X bar W in the book, it's not labeled by an equation, but it says it's the summation from I equals 1 to n of the WI times the XI divided by the summation of I equals 1 to n of the WIs. So here, right, we have our weights, those are our WIs, and then we have our temp $X expanded. Well, really, those are our XIs, right? And then on the denominator, we have the temp of X dot expanded. That is your, those are your X's again. So actually, this is a mistake, right? This should actually be the weights in the denominator to get the X bar W. So let's just fix that up real quick. Sorry, I missed that. fit.glm $weights. So it's always good to just triple check your notes and make sure that you've used the correct equations throughout. So, okay, now our X bar W should look more correct. All right, that's looking good. Now, for the standard errors that we're about to calculate, we're going to also need the the weighted sum of squared deviations about the mean, right? That's our SSW. So from the book, we can see that we're going to take our weights and we're going to multiply that by our xi's minus our x bar w's. So we get our SSW. All right. And now we can start to use 11.6 and down. So we're going to first calculate the estimated standard error for alpha hat. And the way we calculate that is by taking the square root of 1 over the sum of the wi's plus our x bar w squareds divided by our weighted sum of squared deviations about the mean, the SSW. So we get our standard error of alpha hat, 0.0909. And then we can calculate our estimated standard error for beta hat. And that's 1 over the square root of SSW. Okay, looking good so far. From equation 11.8, we can get the covariance between the estimates of alpha hat and beta hat. That's going to be our negative x bar w divided by the SSW. So we can get our covariance between the two estimated parameters. And that's 0.00019. So all of this looks really nice. If we would have taken summary of fit.glm, we would have already been able to pick off the standard error of alpha hat and the standard error of beta hat. So essentially in the back end in R, they've done all these calculations. So first we said, okay, well, what if we wanted to do the calculations ourselves? But really at the end of the day, you don't really need to do any of these calculations in practice because you're going to just use this summary of fit.glm to get your standard errors. But it's nice to verify that you get the same exact answers. So you know what's going on behind the scenes and how are things calculated and what do they actually mean in those standard errors, right? So we can also take the names of summary of fit.glm because essentially there are certain things that we can pick off of fit.glm with a $sign, but there's might be other things that we could pick off of summary of fit.glm. So we're going to ask ourselves, what can we pick off? And if you notice, we have new things available to us. Look at that: covariance unscaled, covariance scaled, coefficients, degrees of freedom, what family was used. There's lots of different things. So let's just pull off the coefficients, for example. Now that simply gave us only the coefficients table versus all of the information that we got before. So this can be really nice for report writing. If you ever want to pick off very particular values to insert into a report, then you may want to pick off the coefficients just by using that $sign. All right, if we notice, we can also pick off the covariance matrix, the variance covariance matrix. So right on the diagonal, this is the variance for alpha hat and beta hat. And then the off diagonal, notice that's the same as the covariance between the estimates of alpha hat and beta hat that we calculated by hand before. So there's multiple different ways to get to the same exact things for equation 11.6 through 11.8. So it's really up to you what you prefer to use. So once again, it didn't matter if I use this negative x bar w over SSW, or I could just say, hey, remember I fit that GLM? Pick off the covariance unscaled and give me the second row and the first column. And either way that you do this, you're getting the same exact value. So it's really up to you and a preference for how you like to code of how you're going to do it. Are you going to hard code equations or are you going to use built-in functions within R? All right. So we can go on and we can say, what if we want to calculate all of this directly, right? We can. First of all, what is the sample size of our data set, right? We already saw that we had 756 rows in our data set, right? We can calculate the probabilities, right? Those are our PIs. And by doing that, we can get each of the individual probabilities, right? And then we can calculate our W's directly, right? And this is corresponding, if you're following along in the textbook, 11.12 and 11.13. All right, so we can get our W's, and from here, I'm going to make a plot, and I'm going to just plot the W's we just calculated with the weights from the GLM model. Because essentially, if the textbook is saying you should be able to calculate your weights in a particular way, and we use that formula, and then we use R to fit a GLM and get the weights, those should lie exactly on a line if we've done everything correctly. Okay, so we're going to double check, and voila, we have everything directly on a line for those W's. Okay, so this is good news because what R is calculating and what we calculated by hand is exactly the same. All right, so now what we're going to do is we're going to do some more things by hand. We're going to take and make a design matrix. The design matrix has one column of all ones, right? So we're going to repeat a column of ones n times. Remember, n is the number of rows. And then our x expanded, those are all our x values. So those are the ages in this case. So I'm going to create my design matrix x. And if you wanted to look at the first 10 rows of x, you could say x 1 to 10, comma, and hopefully we see here's our first column, all of ones, and then our second column should be the ages. And since we're looking at the top of x, we're starting with negative 2.5. And if we looked at the bottom of x, we should eventually get to positive 2.5. All right, we're going to calculate V by making a diagonal matrix, right? Where we have 756 rows. And on the diagonal, we're going to put the weights, okay? So essentially, off the diagonal is going to be 0, and our weights are going to be on the diagonal. Okay, so that's giving me V. And if you're interested, you could look at the first 10 rows of V just to confirm that, yes, this is a diagonal matrix. Ooh, that's very large. Maybe it's 756 by 756, right? So let's look at the first 10 rows and the first 10 columns because that just got very huge to look at. Okay, here we go. Awesome. So we have a diagonal matrix. The weights are going on the diagonal. The off diagonals are all 0. Okay, now to calculate the variance, we could do X transpose VX inverse. Okay, so in R, when we use solve, that is calculating the inverse. If we use the T function, that's really giving us the transpose. So really, if we wanted to read this the way we'd be used to, it would be X transpose VX inverse. And that is giving us our variance. All right. And notice that this variance covariance matrix, that looks exactly like we pulled off from summary of fit.glm, right? Remind ourselves, right? This gave us our variance covariance matrix, or we could have calculated it by hand. But either way, it's pretty nice to know that you can do it by hand in R. I still wouldn't want to do this by hand with 756 people without using computing, but we can do this by forcing it hard coding everything, or we could say, hey, I bet there's some built-in functions in R to do what I want. I'm going to use those functions. All right, so we're going to reverse back slightly and go to the confidence intervals, right? So we are going to want to calculate a confidence interval for the slope and intercept of the logistic regression model. And to do this, we're going to need a standard error for alpha hat. And we're going to need a standard error for beta hat as well, right? So we're going to set our alpha level at 0.05 because we're going to build 95% confidence intervals. We're going to use the Q-norm function. Remember that the Q-norm function says, if you give me an area, and since we said lower tail equals false, if you give me the upper tail area, I'm going to give you the critical value associated with that upper tail. So that Z crit value is 1.96. All right, alpha hat, remember, we could pull off the coefficients. And if we look at that table real quick, right? Alpha hat is really in the first row and first column. So we're going to just pick off the first row and first column. We're going to save that as alpha hat. If you want to verify that that's correct, just go ahead and type in alpha hat and run that in. And you can see that that's negative 1.25. You can verify some of these numbers as well on page 294 of the text. In that middle paragraph, it's showing you, it says the coded age is 45 minus 30 over 5 equals 3. And this is the estimated log odds. And you can see that they have the alpha hat plus the beta hat times 3. And we got the same exact alpha hat of negative 1.25. All right, so for the confidence interval for alpha hat, all we need to do is do alpha hat minus Z critical times the standard error of alpha hat, and then alpha hat plus Z crit times the standard error of alpha hat. That is going to give us our confidence interval that we're interested in. Okay, similarly, we could get a confidence interval for beta hat, right? Remember from these coefficients, right? If we look at the coefficients down here, the beta hat is really in the second row and first column. So here we're going to pull off the second row and first column of the coefficients to get our beta hat. Okay. If we type in beta hat, we get 0.3470. Okay. Our confidence interval for beta, we're going to take our beta hat, subtract our critical value times our standard error, and then, ooh, typo again. That should be a beta hat plus the Z critical times the standard error beta hat. Okay, so when we put that in, we get our confidence interval goes from 0.21 to 0.48. Okay. This is looking good so far. All right, what do we do next? Well, like I mentioned before, on page 294, they talked about making a prediction for someone who is 45 years old. And if they're 45 years old, that equates to an X value of 3. Okay, and they did that by standardizing the 45. 45 minus 30 divided by 5. All right, so we're going to set x0 equals to 3. All right, and then we're going to calculate a prediction for that person. Okay, now we can use this predict.glm function. We just have to say, hey, this is the model, fit.glm, and I have a new data set. It is where my x.expanded is equal to 3. And since we set x0 to 3, I can just say x.expanded equals x0. All right, so from that model, we get negative 0.2127, just like what the book has. All right. If I want to, I can use that exponent function to exponentiate the logit, right? So I'm going to exponentiate that value divide it by 1 plus the exponential of the same value. And that will give me the estimated probability for a woman who is 45 years old. Okay, so I get a value of 0.4470, right? This is really the estimated proportion. Similarly, in the textbook, they show you that you could have calculated this by doing 1 divided by 1 plus the exponent of that logit p hat x0. Should be a plus sign. And from here, I should have a negative sign right in front of that. And I believe that should give us the same exact value. If we've done everything correctly, 0.4470. Okay, looking good. So it's really up to you which one you'd like. I think the second one is a little easier to hand code. But once again, you have options. All right, so we're going to calculate from equation 11.9 the standard error of the logit for a new prediction, right? So our new prediction, we have already found that, but essentially here, we still need to hand code that standard error using equation 11.9, right? So if you notice, we have our standard error of alpha hat squared. We have 2 times x0 times our estimated covariance, and we have our x0 squared times our standard error of beta hat squared. So this is giving us our standard error for the new prediction. And when we do that, we get a value of 0.2311, looking good so far. Okay, we can get our standard error of p hat x0, right? And that is an equation 11.10, where we do p hat x0 times 1 minus p hat x0 times the standard error of the logit of p hat x0. All right. So as we run that in, we can get the standard error of p hat x0. And then we can get the confidence interval for that new prediction, right? So we can calculate that by doing the logit of p hat x0 minus z crit times the standard error of the logit, and then the same thing, but instead of minus the margin of error, you're going to do plus the margin of error. Or similarly, we could calculate the confidence interval for p hat x0 directly by doing p hat x0 minus z crit times the standard error of p hat x0, and then p hat x0 plus the margin of error. And I can get the confidence interval for the predicted probability. Okay, if I wanted to, I could double check that if I exponentiated the confidence intervals and then divide that by 1 plus exponentiating that confidence interval, look at that, we get the same exact thing. So it's really up to you, right? You could say, I could calculate a confidence interval for the logit of p hat x0 and then just take the x bit and essentially back transform to get the confidence interval for p hat x0. Or I could calculate the new standard error for p hat x0 and calculate a confidence interval directly for p hat x0. Either way, you're going to get pretty much the same exact values. They're slightly different, but in practical terms, it doesn't really matter which one you use the majority of the time. All right, so this has been a lot, and so I want to make sure that you take the time to code this through. Try some different examples with some different maternal ages, right? Try to read it through. Decide, hey, am I going to hard code functions and equations from the textbook? Or am I going to find a way to use built-in functions? Really, that's all up to you. But I hope you learned something today. And that is really Chapter 11, Section 3, Part 1. A closer look at some logistic regression models. Have a great day.